Welcome to Energy Talks, a regular podcast series with expert discussions on topics related to power system testing, data management, and cybersecurity in the power industry. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. Rotating machines such as generators and motors are exposed to thermal, electrical, ambient, and mechanical stresses during operation, which can alter their condition and performance over time. Periodic tests and inspections are recommended to detect faults that can damage critical components of the machine, which may need to be repaired or replaced to ensure continued reliable operation. In previous Energy Talks episodes, I spoke with OMICRON rotating machines testing expert Fabian Öttl about the recommended periodic tests that can be performed to detect faults and prevent serious damage and failure in machines. In this episode, I've invited Fabian to join me again to talk in detail about electromagnetic imperfection measurements, which are performed to assess the condition of stator cores in machines. Fabian describes the importance of these measurements and how they are performed. Specifically, he describes how he worked with customers to develop an easy-to-use measurement solution performed with OMICRON's CPC multifunctional testing device and primary test manager software. Hello, Fabian. Welcome back to Energy Talks.
It's good to be here. Thanks for the invitation.
Well, it's great to have you here. Fabian, what is electromagnetic imperfection testing, also known as ELCID, which is performed for stator core condition assessments?
Thanks, Scott. That's, I think, a very good question. It sounds a bit complicated sometimes. Nevertheless, at the end of the day, it's a very easy principle. We would like to detect any issues in the stator core of rotating electrical machines. As you mostly know, or definitely know, stator cores of rotating machines are composed by small laminated steel segments which are isolated against each other. That's because of the manufacturer or as well the operator wants to minimize the eddy current losses. Mm-hmm. So if you have an issue there, it can happen that local hotspots occur, and therefore we would like to test the electrical machines to avoid such hotspots.
Okay, very good. When you say machines, what types of machines are tested for this?
Actually, any type of machines. We designed our solution, so we do have a solution about that for bigger stators like bigger motors or hydrogenerators or turbo generators as well. But we have examples where users did some measurements on small motors as well. So there are basically no limits about it. But of course, as I said, we designed our solution for the bigger rotating machines.
So why is this measurement so important?
Well, if you imagine if there's a weak spot in this isolation against or between the lamination, the steel laminations, you can imagine that there are higher eddy currents occurring, and higher eddy currents normally means that local hotspots can evolve. So they start basically on a certain spot and then they can grow. And if they're becoming bigger and bigger, they can lead to a partial core melt of the machine and therefore total damage basically of the stator.
So you mentioned a gradual process where stator cores could be damaged.
Yeah.
A company receives a new machine. How long does it take for these types of problems to actually develop? What conditions are influencing that development?
That's difficult to say for each and every stator, of course. What conditions can start such things are like you have a lot of ambient mechanical and electrical stresses, of course, in rotary machines, as this happens as well for insulation in the stator cores. More vibration, more mechanical things rather than electrical things in this case, of course. Then you can have issues during manufacturing processes. You can have as well some scratches during inspection issues. You can have weak spots during rewinding of the machine. So if you're removing the wedges, you can as well damage your stator core. Or a very common fault or a very common thing is as well, if you have a fault to ground, so high voltage to ground fault, and the fault current which is flowing can partially melt already a small portion of the stator core and initiate such mechanisms. So also if you have a small or if you have a phase to ground fault, even if the protection immediately trips, you'd always investigate your stator for such damages as well, not just for the insulation damage, but as well for the stator core damage as well.
So given this, it makes sense to do the measurements periodically. So when exactly do you perform such measurements on the stator core?
Actually, we recommend a period from between 5 and 10 years. Usually when you have a bigger maintenance, when you're pulling the rotor, you are going for such a check as well. It's not really possible to have kind of these things online monitored, because that's simply not possible. Only very, very locally maybe, but even that is not really an option usually. And therefore you do it like on a regular basis for every bigger maintenance period.
So how exactly is the measurement performed?
What are you doing is you are basically injecting a small portion of the rated flux in the stator core. And with this small portion, you excite the stator core usually to 4% of the rated flux. With this 4%, you will see stray flux, or higher stray fluxes, once stator core fault occurs. And this is measured by Chatok coil or Lukowski coil, depending where you are. And you are going to scan the whole stator surface with this Chatok coil, basically the whole circumference, the inner circumference of the stator.
Okay.
And any change in this stray flux is then indicated by the quad current. The quad current is basically the current which is 90 degrees phase shifted to the one you are injecting.
Very good. So what measurement challenges have helped to develop the OMICRON solution for these electromagnetic imperfection tests?
It's an interesting question. We got actually approached by one of our customers. They wanted to know if we are able to perform some ELCID measurements with the CPC 102. And at that time, we didn't have any solution available, actually. But I started to think a bit about, and I thought, maybe this could be a very interesting topic for the multifunctional device, which the CPC is actually, to explore another measurement as well. We were very lucky at that time because like 2 weeks after the customer approached us, another customer was in Klaus in our headquarters for a visit for another topic. And we started to talk, and they said, well, if you would like to try that out with the CPC 100, come to our workshop, because we have currently a stator there which has an issue on the stator core. And we went there and made the proof of concept. And this was like now already 8 years ago. Then it took us, of course, some time to develop that. And we have now our own solution. What we put special focus in this solution was actually on usability and ease of use for the customer, beside, of course, high accuracy, high reproducibility, as always, I would say. But especially in this particular case, that was very essential, because the initial customer which approached us, said the currently available options or solutions on the market are very cumbersome to use. And that's why we put here an additional extra effort in. And I would say this was kind of, we had success in that, because one example shows that we launched the solution during the COVID pandemic, and it was not possible to travel to the customer and show the customers the solutions. So we sent the solutions there, and the customers performed the demo measurements, the first trial measurements, actually by themselves. So that really shows how ease of use is our solution in this case.
Very good. So could you, again, emphasize what the key benefits of the OMICRON solution are?
Yeah, of course. So we have a semi-automatic scanning of the stator core, meaning, as I said before, this coil needs to scan the whole stator inner circumference. Therefore, we introduced the semi-automatic scanning of the stator core by a rail, so to basically improve the usability. The measurement and the excitation is in one solution. So you have a turnkey solution, basically, with the CPC 100 and the accessory, which offers a turnkey solution for this particular measurement. We are independent from the grid, so we have frequency variable injection from 15 to 400 hertz. Especially 400 hertz is very interesting for some customers to basically improve as well the signal to noise ratio. And we have a very user-friendly workflow using our primary test manager software, which gives you a maximum of guidance, and as well one-button reporting and all the feature you anyhow have in PTM. We can easily extend our excitation solution, excitation cable basically, to meet any specific requirements. And of course, you have the CPC100, which is not just measurement device for this particular test, so for the particular ELCID measurement, but offers you a wide area of multifunctional testing. So I think that's more or less the key advantages of our solution.
Okay, so you can essentially use the same base solution for other types of tests, electrical tests on rotating machines.
Exactly, and not just rotating machines, but as well power transformer, CTs, VTs, circuit breakers, any type of asset you can imagine in the power industry.
Okay, perfect. Very universal.
Yeah.
So how long does it take to perform these measurements?
It's actually not a fast measurement, I have to say, but compared maybe to the rated flux probe, which can be seen as an alternative for this measurement, it's much, much faster and much easier to implement. Sometimes for the rated flux measurement, you need to have a single phase source, which is basically supplying all the power you require to energize your rotating machine. And this is sometimes even not possible. So it's much, much faster there. But you cannot really say it takes like 2 hours, it takes a full day, because this is really depending on the size of your generator, the size of your motor. But nevertheless, what I can say is that we really focused on usability, we really focused on speed up the measurement. And therefore, I think I'm not afraid of any comparison between alternative solutions or methods.
Okay, very good. Quick question about practicality here and how long it takes to perform these measurements.
Yeah.
Is this a measurement that one person can perform, or does it require two people to perform the measurement?
Actually, we put some focus as well on the single person approach, basically, that one person only can perform the measurement. There are no high voltages there. So also from a safety point of view, it's not really dangerous. So one person can perform it. Of course, it's easier to have a second one there as well. But in principle, one person can use this device, also with the possibility of steering it, so to say, not directly from the laptop, but as well within the Stator core with the push button approach, with the PTMate approach, which is our app, which is then connected to the PTM actually, and gives you an additional benefit in terms of usability.
Okay, very good. So how do the results help users decide what to do? And what is actually done to rectify the situation if any problems are found?
Yeah, that's a good question too. That's a very important question also. I often got them from customers. As I said before, the quad current is basically the indication of how much current flows in this fault location, so to say, or potential fault location. And in the community, there's a kind of an agreement that if this quad current is higher than plus or minus 100 milliamps, then you have to at least investigate this spot, basically. If it's even higher than 300 milliamps, you have to do definitely something. But usually this 100 milliamps is kind of a limit which is widely accepted, so to say.
Okay.
Then it depends, of course, what kind of issue you have. If it's really located one on the surface, you can do it with chemical etching. You can maybe insert some microflakes if it's, for example, a very old machine which is still paper insulated between the laminations. It's one option. If it's down in the slot bottom, for example, which is also detectable with our solution, again, you might remove the winding and then do it with chemical etching and so on. If it's deeper in the Stator core and Stator core itself is already not the best anymore, it might be one reason for the decision of purchasing a new Stator, for example.
Okay. So how do you actually see the results of the measurements to make these types of decisions?
Yeah, that's again, the quad current is very important in this case, and we display the quad current in two ways. One is basically a kind of a old-fashioned, I would say, a graph where you see on the bottom basically the distance from your starting point, and on the y-axis there is displayed the amplitude of the current, and then you see directly where the peaks are. You can of course compare these quad currents as well with the slots measured in the Stator core, and beside this global limit I was talking about is 100 milliamps. And then in addition to that, you have the possibility of display the whole Stator area, so the whole inner area, via a so-called heat map. That's a false colored map where you can set your threshold, and everything above the threshold is then displayed in red, and everything below is displayed in green or yellow. And that's also quite convenient to see immediately where potential hotspots are.
Okay. And so you do recommend that once hotspots are detected or indicated, that you do a visual inspection to verify.
Yes. That's visual inspection is definitely the first and the easiest one to perform. And if there's something there, you can easily repair it. If not, it depends a bit on how high the amplitude of the quad current is. You can also leave it and check it next time and check if it became more severe or if it stood the same. And so that's basically the usual approaches you have as well for other measurements too.
Let me just verify one thing. I could imagine that there are developing hotspots that maybe haven't left a visual trace yet, but they're still important to know about. And these are the types of things that you could readily detect with a measurement.
Exactly. For example, we had one customer example where they were measuring on a very large turbo generator and above 200 megawatts. So with visual inspection, they just saw a very, very small scratch on the surface of it. So you would never really even think about that this could be an issue in terms of this particular fault. Then they did the measurement with our solution, with our ELCID solution, and at the end of the day, it turned out that exactly this hot spot was basically at minus 300 and something milliamps. So it was a really severe hotspot or potential hotspot during operation. And it turned out to be a very good success story as well for them because they were on site. They could do the repair immediately. So they had no delay in terms of going back to operation again. They did some chemical etching there and then everything was fine. And they could as well verify with our solution afterwards that the repair was successful.
Very good. Okay. Do you have any other interesting customer stories to share with us about ELCID testing?
Yeah, we have many of them. Maybe one was with a bigger motor where the customer or the operator experienced a face-to-ground fault. But from the outside, they pulled the rotor and from the outside, there was nothing visible really. So actually, it was our measurement which detected where the fault was because this fault current caused connection basically between at least two or even more laminations in the slot bottom. And that's very challenging to see. For example, with the rated flux measurement and the thermographic camera, it might be the case that you will not detect it. So with our solution, that was possible to see. So they could really detect as well the spot where this happened. They verified that with the endoscopic camera from the back iron, basically, in the ventilation duct. And they were very happy actually with the result because they could verify that this issue was present before they removed the winding, because removal of the winding is, of course, one potential way or one potential reason for damaging the stator core. So they could really prove to the operator that this was there already before they removed the winding. And they could as well schedule the repair of the stator core itself. And they could as well put that in their offer and everything was fine. And also the operator was happy with that approach. So they knew already that these additional repairs needed to be as well, because otherwise, if you put in just a new winding and then you put it back into operation, it might be the case that you get a partial core melting after a period of time of operation. And another nice story I would like to share is we had on a bigger hydro generator, it was a horizontal machine where we could even leave the rotor in. It was a huge machine, I think something between 7 or 8 meters in diameter. And they had a really, really big structure of supporting the rotor. So the bearings of the rotor needed to be supported in a manner that is basically operation proofed. Mm-hmm. So if they would need to remove the rotor, it took them like a really long time, forever almost. Not forever, of course, but several work weeks back actually.
Interesting. Well,
and they removed the poles only. So they removed a few poles only. In fact, there were 4 poles which were removed. Of course, it was a salient pole hydro generator. Mm-hmm. And then they removed these 4 salient poles, and we could do the measurement with our solution in the gap of these 4 poles. And then they turned the rotor, made the next section basically, and so on and so on and so on. Of course, that was kind of a bit cumbersome, but they said if any other solution, any alternative requires to remove the whole rotor, and therefore it was not possible for them. Also for any robotic vehicle for inspection, it was not possible for them because the air gap was very, very small, which is usually the case in hydrogenerators.
Okay. So now you mentioned that the measurement device itself is mounted on a rail and it moves along this rail automatically, and you can control that with the PTM app. And okay, so the rotor was not removed from this machine, it was left in it. But that means that there was enough room for the person doing the measurement to insert that rail with a measurement device. Is that correct?
In this case, of course, it's a very special situation. You need to be two person at the measurement. One was on the bottom of the machine, one on the top, and then together they removed the rail and put it to the next slot, and so on and so on. They were very happy because they said anything else, any other solution would have been really, really time consuming. So for them, it was like a very benefit.
Okay. So the OMICRON solution for the ELCID measurement, is it used now pretty much all over the world, or do you have a particular region of the world where it's mainly used?
Not really. Actually, we have sold devices in all of the OMICRON regions. So I'm very happy with the acceptance of the device. We have feedback from all over the regions. And of course, we are constantly working on improving the solution with software updates or with additional software features in PTM and so on. But that's, I think, a normal process in OMICRON. Sometimes it might take a bit longer for a particular feature to be implemented. But nevertheless, we are constantly working on the improvement of the device, basically.
Very good. So how can our listeners get more information about the OMICRON solution?
Well, I think as for every OMICRON product, just visit our website or approach us directly, locally, or even in our headquarters in Klaus. I think everybody is happy if somebody is calling or writing an email. And let us know if you have any requests there.
Fabian, thank you for joining me for this Energy Talks episode about electromagnetic imperfection measurements, which are performed for static core condition assessments and rotating machines.
Thanks a lot, Scott. Thanks again. As always, it was a pleasure. Thank you.
Thank you. Take good care.
Thank you.
And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. OMICRON has several years of experience in power system testing, data management, and cybersecurity in the power industry, and offers you the matching solution for your application. For more information, be sure to visit our website at omicronenergy.com. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.